Okay, so for this second video tutorial, I thought it would be fun to just pick up where we left off with the voting rule and modify this bit of code until we have some kind of completely different, maybe more biologically interesting model. So I thought it would be fun to make cells swim up a concentration gradient. So what I want to do is start some cells on the one side of the grid, initialize a resource gradient and let them swim upwards this gradient, and maybe one cell makes fewer mistakes than the other cell. So there's two types. Alright, so I'm just going to start modifying this, and the first thing I'm going to do is give it a name. I'm going to call it Chemotaxis race. I'm also going to remove the description, and I'm going to kind of change the dimensions because I think the race is fun. It's like a long grid, so I'm just going to make it like 50 by 400, for example. That's a very long grid because I made a typo. Alright, something like this. 500 is also nice, and then I'm going to change the scale to 2. Back to 400. Okay, so like this, but we don't want the voting rule to be applied. So here in the next state we have the voting rule. As I said, all it does is it counts the neighbors that are in state 1 in the 3 by 3 neighborhood. And if that is greater than 4, so that's 5, 6, 7, 8, and 9, then it will become a 1, and otherwise it becomes a 0. That's a symmetrical majority vote rule, which is why you get this nice cow patterns, but actually I'm going to remove it for now. Okay, and so now all we're left with is initial conditions of vote, which are determined by this function sim.initialGrid. If I change this to 0.1, only 10% of the pixels will be white. If I change it to 0.01, only 1% will be white. However, I want cells only on the left side to be initialized. So this function that is kind of nice for if you want to randomly initialize your grid is not going to be useful now. So we're going to have to program it ourselves. Now, I'm not going to explain JavaScript programming in this tutorial. There's very good tutorials on YouTube. Also on my blog, I have a few. So I'm not going to explain this, but what I'm going to explain is basically the thought process. So I need to loop over all the rows and columns because I want to set their states dependent on some conditions. So what I'm going to say is for let I equals 0, I is smaller than sim.encol I plus plus. And then I'm going to open the curly brackets. Open the curly brackets. And I'm going to make another for loop with j, which is going to loop over the rows, sim.nrow, j plus plus, and then curly brackets. Alright, so now I'm looping over all the values of columns, 0 to number of columns, so 399. This is actually 400, but it's smaller than 400, so 399, and 0 to 49. So that is all the possible positions on this grid. So how do I access this grid? Well, it is stored in the grid model, which is called model. So it's sim.model.grid. And if I do I and j, then this is actually this particular pixel. But what we want to do is say, okay, if I is smaller than 10, then I want to initialize a cell here. So that's only all the way in the left-hand side of the grid. So then I could say this dot alive equals 1. Does this work yet? No, it doesn't work yet because we actually are displaying still the vote property. So this display over here is trying to display something called vote, but we only set the alive property. So we have to change this into alive. There you go. Now we have individuals that are all white on the left-hand side, but I actually want it to be random. I want them to be two types and I want to be 50-50. So what I'm going to say is if sim.rng, which is the random number generator, .random is smaller than 0.5, then I'm going to set it to 1, and else I'm going to set it to, just copying it, 2. Alright, so indeed, now we have in the left hand side the first 10 randomly white or red, and I'm actually going to change these colors by modifying this state color thing here at the top. I'm going to say that alive comes in 3 things: black, 1 will map to violet, and 2 will map to gold. Now violet and gold are just, I think they're very aesthetically pleasing to look at. I'm colorblind, so these colors are very friendly for myself, but you can do whatever you want. Okay, but there's something else we should initialize, which is the resource concentration that they will use as a cue to swim in the right direction. This does not depend on being in the first 10. This has to be true for all of them. So what I'm going to say here is, if we're not in this if condition minus I is smaller than 10, I'm just going to say sim.model.grid ij.r. This is the resource. Let's say this is just a resource. Equals 0.01 plus 0.01 times I. Okay, so what did I do here? I'm saying it's starting at 0.01, but for every I, it increases with 0.01. So this starts at 0.01 concentration all the way over here, and all the way on the right hand side it will be, let's calculate 4, so that it will be 4. So 400 times 0.01. Let's save. Now, as you can see, nothing actually is displayed yet about this R variable. But what we can do is we can use the developer console. I'm in Google Chrome, but also Firefox and Brave, they all have this console where you can use Ctrl-Shift-I or a different shortcut for your browser, and it'll open this console. And I made it so that if in Cacatoo you click somewhere, it'll give you the properties of that pixel. And you can actually see that this grid point has an alive 1 and a resource concentration of 0.05. And if everything went well, then if I click here, yeah, now I have a higher concentration over here. And here it should be somewhat 1, yeah. And all the way over here it should be like close to 4. See? So this is working. Something you might notice, though, is that over here the alive property is not set. It's just R. And here the alive property is set. Right? So alive 0 actually currently does not exist. The display actually defaults to 0, being black, but maybe we want to say that if we're not in the first 10 columns, then alive will be set to 0, so that we're sure that alive is set to something. So now if I click over here, alive is 0. I somehow managed to exactly click resource concentration 1. Okay. So that's that then, but now we might want to display this R resource concentration. So maybe just very simply, let's copy this display function and let's set the property to be displayed, which is the second argument for this function, to R. Okay, that didn't work. Why didn't that work? The create display is meant for discrete variables, and what we have here is a continuous variable. So you see indeed that the pixel number 1 that I happened to accidentally click just now is shown as 1, and then exactly where it's 2, it's blue at 3. Okay, so we need a different way to display this, and for this we can go into the documentation and take a look at the display and colors tab, because this has all the different ways to display things. It also shows you all the available colors actually. So what we need is a display continuous, which is a modified version of the display that has way more options. I'm just copying the one with all the options already in there so that we can just modify those options until it displays what we want. So I just pasted it in here. Which model? Well, the model is not called Turing, it's called model. Horrible naming, but anyway. The property we're showing is R. And the label, which is just a text description, will be resource concentration. Sorry. I'm just going to hit enter here because otherwise it's going to be unreadable. The minimum value is 0. The maximum value is 4, which we've calculated previously. Then there's the number of colors, which is essentially just in our gradient, how many colors will there be? Well, there's 400 different states, so let's just set this to 400 as well. And then there is the Viridi's fill, which, ggplot and matplotlib, they all like this particular color gradient because it's very easy to see distinct colors variations with this gradient. So I also put it in Cacatoo. The NA color won't be necessary because no values will have the property NA. So I think this should do it. Let's save. Oh, there you go. So now we have our individuals shown over here and a resource concentration shown over here. Okay, and now comes the kind of like tricky part, because now we need a next state function for the pixels that says, okay, if I'm updated, how am I updated? Okay, so for this we need the current pixel. So let's say in the next state, let me equals sim.model.gridij, and let's also get a random neighbor. Let neighbor equals this dot random more 8. And I actually know by heart how this works, but let me show you how you would know. You go in here and then neighborhood retrieval, because we want a random neighbor, and it's this one that I'm actually using, random more 8. More neighborhood is 3 by 3 pixels. It is 8 because the pixel itself is not counted, so it's 9 minus 1. And this is the one we'll be using, which is this dot random more this, because you can actually use it on a different model if you wanted to, but in this case we just want to use it on the model itself, and then ij. So now we have two pixels next to each other. One of them is the one we're currently looking at, and the other one is the neighbor. And what we want to do is we want to swap their positions out if the resource concentration is actually favorable, right? If they're going up the stream. And we also only want to do this if actually the pixel is filled with a living individual. So let's say if me equals me dot alive is greater than 0, which is it's a living entity. It's not black, it is a violet or gold one. And neighbor equal dot alive equals 0. So now we know we're looking at a combination that could be swapped, right? And then what? So naively you might want to say, all right, let's just swap them. So let's say me.alive equals neighbor.alive and neighbor.alive equals me.alive. So we just swap the alive property out. Now, why didn't that work? Now, if I save this, you can see that everything just starts disappearing. What is going on here? Well, we're actually setting me.alive to something and then setting that thing, the neighbor, to that me.alive in sequence. So that actually means that once we set neighbor alive, this one has already been modified, and that's not what we want. So we need a backup of me.alive. So let's say let me alive equals me.alive. This is kind of like a temporary variable that will hold the state of me.alive and use that to set this instead. Still, it's not working. I'm actually wondering why, and I think the reason is because I'm updating synchronously. Absolutely, that's the reason. Okay, so synchronous updating means that the grid will be there will be a backup of the entire grid, and then every pixel will be updated according to the previous state of the grid. Now this is usually this is very good because it means the system is deterministic. There's no randomness or involved at all. The problem is, however, that in this particular case it won't work because individuals will look at the previous state, but that might still contain an individual or an empty spot, and therefore this swapping algorithm will actually not work because they're not updated at the right moment. So instead what we have to use is asynchronous updating in this case. And if we do that, we do see that the system seems to be working. It is not yet dependent on the resource concentration, but you can see these cells are actually swimming around, but they're also turning up on the right side of the grid. And that is because in the configuration at the top, we actually have a wrapping of the right and the top. So I'm actually going to disable all the wrapping, which means there's just a boundary around everything instead of them being able to loop around. Okay, so that actually fixed that problem. But actually it's not dependent on the concentration yet. And you can also see they're not really getting any far. This is really not doing a very good job at this moment. So what we want to do is make this dependent on the resource concentration. I'm going to say that there is a variable called fail chance. And it's defaulting to 0.1. And I'm also going to say that if me.alive equals 2, the fail chance is even smaller. It's 0.01, something like this. So essentially what I'm saying is I'm setting a variable, and for individuals that are individual 2, which are the gold ones, they will fail less often in this swapping. Okay. And then I'm going to say if me.r is smaller than neighbor.r, or fail chance. What I want to do, I want to draw a random number. sim.rng.random is smaller than this fail chance. Then they're going to swap. So there's not a lot of difference right now between the yellow ones and the gold ones. It does look like gold is doing slightly better, but let's make the difference slightly more extreme. Okay, so let's make the gold ones fail with 0.01 and the purple ones with a very high probability. All right. So now you can really see the difference here. The yellow cells are really good at swimming upstream, and the purple ones are kind of just bouncing around. I'm just gonna wait and see how this settles, because I actually never made this before. I just kind of wanted to show you the process, including all the weird bugs and errors that I had to fix. Oh yeah, now they're just kind of hopping around, because even though they're already there, they're still failing a lot. Okay. And the yellow ones are just kind of squeezed in there and not able to move. Alright, so that's it for this tutorial. Feel free to add stuff yourself. You could, of course, make this different. You could also say that this fail chance is something that maybe is evolvable, and then you can let them race to the right and then say, okay, I'm just going to select the ones that made it and set them at the beginning again, and then you'll have your own evolutionary process where they will get better and better at racing to the right if you do that correctly. Alright, have fun.